In section 17.2, we start talking about electrochemical cells, and in particular we're going to be talking about a particular type of cell called a galvanic cell. So if we couple an oxidation half reaction by an external circuit to a reduction half reaction, we form what is known as an electrochemical cell. And what I mean by that is that we're going to have two containers, and in one of them an oxidation reaction will occur, and then in another container we're going to have a reduction reaction occurring in its own container. And then what's going to happen is any electrons are going to flow via what we call an external circuit, and also any ions that need to move in order for the reaction to occur will also flow via an external circuit. So this will make a little bit more sense as we move through describing what these cells look like. So when we do this, we construct what's referred to as an electrochemical cell. And electrochemical cells can be divided into two categories. There are what are referred to as voltaic cells, and in voltaic cells the overall cell reaction is spontaneous. That is that electrons will be spontaneously lost and electrons will be spontaneously gained. And so for a spontaneous reaction, as we know, delta G will be negative. And these are what we're talking about when we're talking about galvanic cells. So in a galvanic cell, the electrochemical reaction is spontaneous. And the cool thing about these types of cells is that we can intercept that movement of electrons and use them to do electrical work on the surroundings. So a classic example of this type of cell would be a battery. The other type of electrochemical cell are what are referred to as electrolytic cells. And in an electrolytic cell, the overall cell reaction is non-spontaneous. That is, delta G is positive. And in order to get the reaction to occur in the oxidation and reduction reaction to occur in these cells, we have to input energy. So a good example of this would be electroplating, when we're coating an object in a metal. So sometimes we want a reaction to occur, but it's not spontaneous, and we can get it to occur by inputting electrical energy. When we're doing that, what we will create is what's referred to as an electrolytic cell. So both types of cells contain what are referred to as electrodes, one for each compartment, and these electrodes conduct electricity. Electricity is just the movement of electrons, and so these electrons are going to move from one compartment to the other. So the electrode at which the oxidation half reaction occurs is referred to as the anode. That's where electrons leave, right? Because oxidation is loss of electrons. So electrons will leave a cell compartment at an anode electrode. The electrode at which reduction occurs, remember the reduction is gain, that's where electrons are going to enter into the cell compartment there. So that type of electrode where the reduction is occurring is referred to as a cathode. So electrons are going to move from an anode into a cathode. That's what's going to happen, right? So electrons go anode to cathode, A to C. And then those electrons, they're going to be either removed from our cell compartment or added to our cell compartment. Okay. So the electrodes, they need to be immersed into something that's conducting, a conducting mixture of ions. Most commonly this is an aqueous solution, and that's referred to as the electrolyte of the cell component. So each of our two electrons is going to be immersed in an electrically conducting mixture of ions referred to as the electrolyte. And so the anode is connected to the cathode via a wire, and electrons will spontaneously move from the anode to the cathode in a voltaic or galvanic cell. Now, it gets a little bit confusing. If the anode kept losing electrons, it would build up a greater and greater positive charge. And if the cathode kept gaining electrons, it would build up a greater and greater negative charge. And then, well, why would electrons be lost for something that had a big, huge positive charge? That would never happen because positive charges attract electrons. And then why would electrons flow towards something that has a negative charge? Because things that have negative charges repel electrons. So this would never work. And so how we get around this, or how we make this flow of electrons continue, is by installing what's referred to as the salt bridge, which is a source of positive and negative ions. And what's going to happen here is that for every electron that is lost, we're going to put one anion back into the anode compartment. And for every electron that is gained, we're going to add a cation from the salt bridge into the cathode compartment. So we've got electrons moving through the wire connecting the two electrodes, but then we've got anions moving through this thing called the salt bridge, anions and cations moving through the salt bridge. And anions move towards the anode and cations move towards the cathode. If we don't have the salt bridge, our cell will stop functioning pretty quickly. So, in a voltaic cell, the anode has an excess of electrons or an excess of negative charge in comparison to the cathode. So we label it with the negative symbol. Now, the cathode is deficient in electrons. It doesn't have enough negative charge. It is relatively positive compared to the anode, so we label the cathode with a plus sign. So the anode is labeled as the negative electrode, and anions move towards the anode, but electrons move away from the anode. The cathode is labeled as the positive electrode, and cations move towards the cathode, and electrons also move towards the cathode. At the anode, we're losing electrons, so it is in the anode compartment that oxidation is occurring. At the cathode, we are gaining electrons, so it is at the cathode that reduction is occurring. So the salt bridge serves to complete the circuit. Anions move from the salt bridge into the anode half cell compartment to counter the loss of electrons, and cations move from the salt bridge to the cathode to counter the gain of electrons. Pretty quickly you recognize if you set a cell up and you don't have a salt bridge, nothing happens. In the absence of the salt bridge, electrons do not flow. So what do we normally make the salt bridge out of? It has to be something that's a source of ions. It has to be electrically conducting. Sometimes it's like a kind of a pasty material or a gel, but most commonly what we'll do in the lab is we'll take a piece of filter paper and we'll wet it with an aqueous solution of an ionic compound to make a salt bridge. Okay, so by convention, we normally draw the anode on the left of our cell and the cathode on the right, and by doing that, we have electrons flowing left to right from our cell. So the anode is always labeled as being the negative electrode, the cathode is always labeled as being the positive electrode. As I mentioned, oxidation occurs at the anode, reduction occurs at the cathode. Cations move through the salt bridge towards the cathode, anions move through the salt bridge towards the anode. So that's a kind of a classic sort of setup. The solution that contains the reactants in each cell compartment is referred to as the electrolyte. These guys here are called electrodes. And electrons flow out of the cathode, and electrons move from the through the anode into the external circuit. Okay. In some cases, the electrodes themselves are reactants. These kinds of electrodes are referred to as active electrodes. In other cases, the electrodes are made of things that conduct, but they're not chemically reactive. They're not part of the reaction. These are referred to as inert electrodes, and classic examples would be graphite or platinum. So inert electrodes is one name. They're also referred to sometimes as inactive electrodes. If the reactant that is undergoing reduction or oxidation is a solid, then and it's electrically conducting, then that's a perfect material for an active electrode. If our reactant that's undergoing oxidation or reduction is a liquid or a gas, or it's not particularly electrically conductive, then it's going to be hard to attach a wire to it. It's going to be hard to fashion into an electrode, and in those scenarios we'll probably use an inactive electrode. Alright, so a classic example of a voltaic cell is the copper zinc cell. So what we have in this cell is we have an anode compartment that's comprised of a piece of zinc, which is an active electrode, immersed in an electrically conducting solution called the electrolyte. And then that is connected via a wire to another compartment, to the cathode compartment, where we have a copper cathode immersed in an electrolyte solution that contains copper 2+ ions. And then to complete the circuit, we have a salt bridge linking the two compartments. And so what happens is zinc gets oxidized to zinc 2+, giving up 2 electrons, and then the copper 2+ that's in the electrolyte on the other side takes on those 2 electrons and forms copper solid. So what we'll see in this cell is that the zinc electrode will get smaller. This one will be eaten away. And the copper electrode, because we're making solid copper, will get bigger. So that's kind of cool. As we're consuming copper 2+ ions, which have a nice blue color, the color will fade. So the blue color fades, which is kind of interesting. So you can actually see this reaction sort of occurring if you leave it running long enough. Now electrons will move from the anode to the cathode, and if we want, we can kind of intercept them, and we can actually use these electrons to maybe like light a light bulb or something. Alright, so it's a kind of a really simple cell to make. So what happens at the anode is that the zinc is oxidized, and the zinc that's being oxidized is actually the electrode. It's an active electrode. At the cathode, what's happening is the copper 2+ is being reduced. So overall, this is our balanced redox equation. So what happens? The zinc anode gets eaten away, and the copper cathode grows larger. So it's kind of cool, and you can actually see this happening before your eyes. So if I wanted to draw a diagram indicating exactly what was happening here, it'd be quite a lot, wouldn't it? Right? It would be, there would be a lot going on here, and I haven't actually even identified how the anions and cations are moving. There we go. So, to describe completely what's going on, I'd have to draw a diagram that looked something like this, and I'd have to put these two equations in here, and yeah, it's just a lot. So because it's kind of awkward to describe voltaic cells every time by making these sort of complex diagrams, we have a shorthand notation which is called cell notation that we've developed. And in cell notation, what we do is we write the anode on the left and then the cathode on the right, just like we do in our diagram, but we just use symbolism to indicate the reactions that are occurring. So I'll show you what that looks like now. So in the notation for a voltaic cell, we write the components of the anode compartment on the left in the order that they appear in the oxidation half reaction. So for us, we're going to go zinc solid goes to zinc 2+ and 2 electrons. Okay, and what I do is I'm writing the two species other than the electrons here that appear in this half reaction. And what I do is every time there's a change in physical state or phase, I put a vertical line. Okay, so this is notation representing that reaction there. So those two things are equivalent. What I do now is I write a double vertical line and then I write what's happening over in the cathode. Okay, so put a double vertical line and I write what's happening in the cathode. So how I write out what's happening in the cathode is I wrote out the components of the cathode in the order that they appear in their in the reduction. Actually, I should say reduction half reaction. So what's my reduction half reaction? Copper 2 plus 2 electrons gives copper solid. And again, every time there's a change in phase or change in state, what I'm doing is I'm putting a single vertical line. So there's my anode, and there's my cathode. Okay. Now sometimes we'll have like multiple components in the same phase, so we'll have multiple things that are in the aqueous solution. If we do, we're just going to separate those by commas like so. Generally we're going to have the electrodes are going to be on the outer edge, and that's a good sign that you've got things written correctly. Okay. If you do have inert electrodes, they're always placed on the outer edge.